Hello everyone. In this video, I'm going to do my best to show you where a confidence interval comes from. So how did we get this idea to give an interval of values that the true proportion or the true mean could be? So this is the foundation behind what we learned last time, and it is the explanation of where this formula comes from. Okay, here we go. So a confidence interval is an interval of plausible values for a population parameter. So that could be the proportion, that could be the average, we could be estimating a minimum or a maximum. Whatever information we want to know about the population, a confidence interval will give us a range of plausible values for that piece of information that we would like. So let's remind ourselves what plausible means. Plausible means that it's reasonable or believable based on the data. And this based on the data is an important element. So as with many things in this class, we're going to investigate where confidence intervals come from by working through an example. So the table shows a random sample of the ACT scores from 20 college freshmen taking calculus. So let's take a pause right here and write down what our population is. I'm going to ask you a lot of questions in this lesson, lesson 61. And even though I'm not with you, I want you to really think about those questions. So what do you think the population is for this sample? So we know that it's college freshmen. All college freshmen. However, it's all college freshmen taking calculus. We have to make sure that we understand that this population is not all college freshmen. Since we only sampled the freshmen taking calculus, we can only estimate the ACT score for college freshmen taking calculus. ACT scores are normally distributed with a mean mu. So we don't know mu because that's what we're trying to estimate. But we know the standard deviation, which is 4.7. So we know true sigma. We do not know true mu. True mu is what we're trying to estimate. This says find the point estimate of x bar and sigma sub x bar. So x bar is the average ACT score for these 20 college freshmen. If we had more time, I would have you enter all 20 of these values into your calculator and run the statistics on it to get the mean. But to save us some time, I'm just going to give it to us. It's 25.05. So the average score for these 20 freshmen taking calculus is 25.05. which is pretty high. Our sigma sub x bar is sigma divided by root n. And this comes from the last unit. We are able to use this formula because it is reasonable that 20 is less than or equal to 1/10 n. Remember, when we use this formula, we typically want to check the conditions to make sure that we're allowed to use the formula. So this condition is the 10% condition, and it has been met. So we're going to take this 4.7, and we're going to divide it by the root of 20. That gives us a sample standard deviation of 1.05. So what that means is that our observations are about 1 point from the mean of 25. So our observations, or our students, are about 1 point from the mean of 25. This is our estimate for true mu. So 2505 is our estimate for mu. Well, we don't expect our x bar to be exactly equal to mu. So we want to be able to say how precise our estimate is by finding the confidence interval. So when we say precise, we're talking about how close to mu we really are. So our estimate from our 20 students is 25.05, but we don't expect that estimate to be exactly equal to true mu. So we're going to build a confidence interval to say how precise or how close to true mu our estimate is. In order to do this, we're going to look at the 68, 95, 99.7 rule for normal distributions. So I have a separate sheet of paper here that I'm going to write this stuff down on, and I would recommend for the most part you just watch and make sure that you remember or understand what I'm saying. And then if you think any of this would be helpful for you, you can go back and put as much of it as you want into your notes. So from the second unit we did, we know that for a normal curve, our mean is in the middle. And then 1 sigma on either direction, in either direction, is 68% of our data. So 68% of our data will be within 1 standard deviation of the mean. Well, 2 sigmas is 95% of the data. And then 3 sigmas is 99.7% of the data. So how do we relate this to the sample that we just took? Well, recall that this sample of 20 students comes from a sampling distribution that has a normal distribution or is normally distributed. So underneath this curve are all the possible X bars that we could find that are sample size 20. This also comes from last unit. So we know, I'm going to say this one more time. We know that the distribution that this sample came from is normal. We also know that the center of this distribution is true mu. That's for sure. That is a given. So we took this sample from a sampling distribution that is centered at true mu. Now we can add on this element that we know that 95% of our samples will be within 2 sigmas of the true value. So based off of this idea that we learned a while ago, we know that 95% of the samples that exist of size 20 will be within 2 standard deviations of the true value. So this idea here, this idea that we know that 95% of our samples are within 2 standard deviations of the true value is reflected in this picture. So they're saying that this is the sampling distribution of X bar. This is the sampling distribution of samples of college freshmen taking calculus that are size 20. So we know that it's likely that 25.05 is within 2 standard deviations of the true value, because 95%, so let me do a little bit of highlighting. This is true mu. This is 2 sigma. This is negative 2 sigma. They're telling you right here that this is 95%. We know that 95% of the samples will be within 2 standard deviations of the true value. So that means that this estimate is likely within 2 standard deviations of the true value. So how do we say this mathematically? This means that 95% of all samples are within 2 standard deviations of true mu. So mathematically, this is represented as the formula mu plus or minus 2 sigma. So this guy now represents our confidence interval. And notice that matches pretty closely the form that we talked about last time, which was your point estimate plus or minus your margin of error. So let's keep building on this. So the next several lines are related. They follow each other. Well, what we use for true mu is X bar plus or minus 2, and what we use for sigma is sigma sub X bar. So these are related. Instead of mu, we use x bar. Instead of sigma, we use sigma sub x bar. Well, echoing last time, x bar we know is our point estimate. Which means that this 2 times sigma sub x bar must be our margin of error. So these things are related. 2 sigma or 2 sigma sub x bar is our margin of error. Okay, well, let's break that margin of error down even further into what we know it to be. So this is our point estimate plus or minus our critical value multiplied by our standard error of x bar. So this now means that our critical value is 2. For this example, our critical value is 2. So I will highlight that. Our critical value is 2. I think for this one, maybe we should write standard error instead of the abbreviation. Well, this is the exact formula for a confidence interval. So confidence intervals are based on a normal curve and the amount of data around the true value. So we know that 68% of the possible samples will be within 1 sigma of the true value, and 95% of the samples that we can take would be within 2 standard deviations of the true value. So now we can build our confidence interval because we now know that this sample, there's a 95% chance that this sample is within 2 standard deviations of the true value. So I'm going to say that one more time. There is a 95% chance that this value is within 2 standard deviations of the true value. So that's how we build a confidence interval. We say our point estimate is 25.05 plus or minus our critical value of 2 multiplied by our standard error of 1.05. If you plug that in and plug that into your calculator and find your lower bound and your upper bound, you get a confidence interval of 2295, comma 27.15. So what we can say is we're 95% confident that the true mu is in this interval. We are 95% confident that true mu is in this interval. So now let's come over here and relate the values to this picture. So Our estimate for true mu is 2505. Our lower bound, or 2 sigmas below the mean, is 2295. And our upper bound, or 2 sigmas above the mean, is 27.15. The distance between mu and your upper bound is your margin of error. So, I'm just trying to see if I have a color that I haven't used yet. Maybe I'll just use pen. This distance is your margin of error. So point estimate is sometimes referred to as PE, and margin of error is referred to as MOE. So this is your point estimate. This is your margin of error. So based on this new understanding, we are going to interpret confidence intervals slightly differently from now on. So we are going to interpret confidence intervals this way forevermore. We are 95% confident that the interval from 22.95 to 27.15 captures the true mean ACT score. So when graders grade free response for the actual AP exam, they are going to be looking for the exact word captures. So the next page of this lesson explains to you why we use the term captures. At this point, you can answer the questions that are below, and when you're done, we will move on, or you will move on to the next part of this lesson.